Guys, good evening, afternoon, or morning. So today we're back at it again with integration, okay? And for this video, we'll be focusing specifically on trigonometric substitution, okay? Trigonometric substitution, okay? Okay. So first of all, what is this trigonometric substitution, okay? What is this trigonometric substitution? So previously in the last video, we've talked about U substitution, right? And we've talked about how it is useful for composite function, right? So for example, let's say you have a example function, right? For example, we're trying to integrate a function where it's just x over x squared plus 1 dx, right? And we know that this particular function right here has no, known antiderivative, right? You can't just find find it in the table, you can't find it, right? It's not possible to find it all. So how are you going to solve it? Okay, is obviously we're gonna take the u value. Okay, I'm gonna put this right. So u value to be x squared plus 1. It's not value, it's more like an expression, right? And then we find the du dx, which is just obviously 2x. And of course, du is just 2x times dx, right? And we want to replace this dx out of the way, so just simply, um, you know, we could just say just half du, okay, equals to x dx. And here's the thing, if you ever notice that this x and dx are already inside the integral, so once we do the integral, what happens is we'll end up having 1 over u times half du, okay? And of course, this half is a constant, you can just bring it outside. So this half 1 over u du, which is obviously half ln modulus u plus c. And don't forget, it's just half ln modulus x squared plus 1 plus the constant of integration. Okay, so that's what we did previously. But right now we're going to do something different. We're going to do trigonometric substitution. And before I actually show you how to do it, let me just dive into a couple of rules actually. A couple of common substitutions that we'll be using. Okay, let's see. Okay, right. So the first form, okay, we have here is if we have an integral whose form is like this, x squared plus a squared, okay, a squared. And now a squared is any number actually. I would say a squared is basically any integer obviously. Okay, we're talking about integer, okay, that is obviously, that is, it can be positive, it can be negative really, but normally we take a that's positive, right? It's a positive integer, so we can say something akin to a natural number, okay? Something what we call a natural number. All right, and that's the first form. Second form we have here is square root x squared minus a squared, if I'm not mistaken. Yeah, square root x squared minus a squared, right? And yeah, the third form, let me just erase this, by the way. Okay, would be something like this. Let me just write right here. It would just be a square minus x square. Okay, so we have these three forms, okay? So if you see your integral having this particular form, what you could do is you could take your x as equivalent to a tan theta, alright? A tangent of theta, alright? And basically, of course, you know your dx d theta when you differentiate with tan theta, you basically would get sec square theta. Okay, you basically get sec square theta. A is just a constant, by the way. Okay, and this tan theta, by the way, all right, it's it floats between negative pi over 2. Okay, so this is like the limits, by the way, all right, and between pi over 2. So this is basically the range, I would say the range of theta values acceptable when you're using tan theta. Okay, and let's say if your integral was in this form, you can use x equals to a sine theta. All right, of course your dx d theta would be um a cosine of theta, right? And your theta is also floating within a range between negative pi over 2, okay? It's less than or equals to theta and pi over 2, okay? And if your last form is like this, your x, you can just replace it with a second of theta, okay? A second of theta. Your dx d theta would be a sec theta times tan theta, okay? And your theta limits are either between 0, okay, to pi over 2, okay, it doesn't actually include pi over 2, or it could be pi between 3 pi over 2, okay. So we'll get on to some examples as to why these limits actually matter, right? Why do we really care about these limits actually, and why are we using these particular forms? Why am I actually using these particular substitution, right? Even the same goes for second theta. And also, why are we using such limits? Why are we exhibiting such limits, actually, right? In a bit. So I just want you guys to actually remember these three forms. It's really important that we do remember these three forms, okay? All right. So with that said, let's actually dive into some questions, all right? Trying to solve these problems together. Okay. So let me go back to the textbook and see some problems regarding this trigonometric substitution that we have here. Right. Okay. So let's see. Okay. So the first question they've given us, okay, from the textbook is that if we're given this integral, okay, of x cubed, okay, x cubed uh times the square root of 1 plus x squared dx, okay? And we want to find the indefinite integral, obviously, right? We want to find the antiderivative, okay? How are you going to find it? Okay, so the hint is obviously from trigonometric substitution, right? And I'll just do this example right away just to give you guys a good understanding. So we can see that the form here is basically root 1 plus x squared, right? So this is actually the form that we discussed earlier, where it's just simply a square plus x square. Okay, a is basically, like I said before, it's a natural number. Okay, so obviously when you have a form like this, then the best thing to do is to substitute x is equivalent to a tangent theta, right? A tangent theta. Therefore, your dx over d theta is equivalent to a sec square theta. Okay. Also, another important thing, a very crucial thing to remember is that I forgot to mention this earlier is your trig identities. So 1 plus tan square theta is sec square theta. And this will be very handy actually, okay? And you'll see in a bit why. So once you have this, right? Or one more thing I forgot to highlight is that you can also rearrange your dx to be equivalent to a sec square theta times d theta. Okay, so you can get rid of that pesky dx right away. Okay, you can get rid of it straight away. Okay, So without further ado, let's simplify the integral. So x cubed would be obviously a cubed, okay, times 10 cube theta, okay, and the square root is just gonna be 1 plus, because 1 is so your a square tan square theta, okay, times with a sec square theta d theta. Okay. One thing I forgot to actually mention is about your a. Right, what is the value of our a here in this case? Okay, because we referred to this particular section, right? We talked about this particular section. Our a actually is here. Our a square is here. This is our a square. A square equals to 1. So, our a is clearly going to be square root of 1, which is obviously going to be 1, right? So, therefore, you can just say this is going to be 1. Of course, it's going to be 1. This is going to be 1. So, it makes things a lot easier, okay? So, therefore, we're just left with 10 cubed, okay? Times, of course, we have square root of 1 plus tan square theta, okay? Times with second square theta, okay? D theta, okay? So that would leave us with what? So we'll have 10 cubed theta, and this is obviously gonna be square root second square theta times sec square theta, okay, d theta, okay, and then we're left with 10 cubed theta times sec theta times second square theta d theta, okay, and then we're left with 10 cubed theta times sec cube theta. Okay, interesting. D theta. Okay, so now we obviously know that second cube and tan cube are related to each other, right? We know that these two, right? They have the identity, right? They have the identity that we have already highlighted earlier. Okay, and I think I might have to erase this, by the way, so that we can have a bit of space. So I'm gonna have to erase this real quick. I'm gonna write this outside. Okay, I'm gonna have to write this out here. Just to keep in mind, actually, I'm gonna change the color to blue. Okay, so we know that um 1 plus tan square theta equals to sec square theta. Okay, so I'm gonna erase this. Okay, so now here's the thing. Okay, here's the thing actually. Um, we're left with tan cube theta and sec cube theta, right? Uh, if we could write, and we know that when we differentiate tan theta, when you differentiate tan theta, obviously, you clearly get sec square theta, right? We do know this, by the way, okay? So these two things we need to keep in mind, by the way, alright? Why you need to keep in mind? Because I'm going to have to rewrite the integral in a very clever way. So we have tan cube theta times sec square theta times sec theta, right? D theta, okay? And okay, what else also I want to highlight? Mm, I can write it like this. Tan, let's see, tan square theta would be obviously sec square theta minus 1 times tan theta times sec theta times sec square theta d theta. Okay. Okay, we're actually coming up with something quite interesting, by the way. And I'm gonna have to erase some parts, by the way. I hope you don't mind. Let me erase this part actually. Yeah. Let me just erase this part so we have more space to do the calculations. Okay. I hope you guys can follow along actually because I know this is quite interesting. Um, what we're seeing here actually is basically tan theta times sec theta squared times sec theta times tan theta d theta. Okay. Very interesting actually, right? Okay, very interesting stuff we're seeing right here. All right, let me think about it a bit. What if I do this? Okay, what if I make it in terms of sec squared theta? So let me just rearrange this, by the way. So let me just rearrange this. I write it like this. I write it as sec squared theta minus 1 times sec squared theta, okay, times tangent theta times sec theta respect to theta. Okay, so what we're left with is obviously um sec to the power of 4 theta minus sec square theta, okay, times sec theta tan theta d theta. Okay, so this is very interesting, by the way, okay? And why am I saying this is very interesting actually is that if you remember, okay, if you remember that if we differentiate sec theta, right? If we were to differentiate the second of theta, we get sec theta times tan theta. So what does this mean? This means that we can go back to a regular U substitution, okay? So I'm going to erase this and show you what I'm trying to explain right away. Okay, so we can go back to a U substitution. I'm going to write it in a different color. I think I'm probably going to write it in, yeah, maybe I'll write blue, whatever. So U is equivalent to sec theta. Du d theta is just sec theta times the tangent of theta. Then du is just sec theta times tangent theta d theta, okay? Which is basically this part right away, okay? And that means our integral becomes far simpler. It's just simply sec to the power of 4 theta is just u to the power of 4 minus u to the power of 2 because sec squared theta is just u squared times du. So integral becomes u to the power of 5 over 5 minus u to the power of 3 over 3 plus c. Okay, and our u is just sec to the power of 5 theta over 5 plus sec cube theta over 3. I said plus, sorry, plus c. Actually, it's not plus, but my apologies. It's supposed to be a minus, but yeah, that's your final answer. Okay? And it's actually pretty cool, you know? Uh, Trig substitution. I know it can get a bit lengthy, but, you know, in some cases it's pretty cool. All right? So let's go to a question. Okay, let's go to a question in the book, which I'll be giving as practice. Okay, so let me erase this. Okay, great. Okay, so one of the questions is if we're given an integral, okay, which is 3 over x times the square root of x squared plus 9 dx, okay? And we're asked to find the definite integral. So I will give you guys the time to pause this video and try to give it a shot and see if you can use the trigonometric substitution method to actually find the definite integral, indefinite integral, my bad. Okay, so assuming that you guys have given a short, so let's try to solve this together by trig substitution. So first things first, let's recognize the form, okay? So we do have a form right away, right? It's just x squared plus 9 square root. So this is basically in this form, right? Which you can write as a square plus x square, and we take our x to be a tangent theta, okay? Here the thing is, our a is what? Okay, a square is 9, okay? This is our a square. A square is equals to 9, so our a is clearly 3. So therefore, we can just write it as x equals to 3 tan theta. Okay? So x equals to 3 tan theta. So when we do the derivative of tan, we get clearly 3 second square theta, right? 3 second square theta. Okay. And we know that dx is just 3 second square theta d theta. Okay? And also, another important thing to remember is the trig identity, which is just simply uh, 3 plus 3 tan square theta equals to 3 second square theta. Okay, so once we're going to our actual integral and trying to solve it, okay, so we get here 3 x as we know it is just simply 3 tan theta, okay, and here is square root, so it's just simply 9 plus 9 tan square theta, okay, times with 3 second square theta d theta, okay. So as we solve it, we get 3 over 3 tan theta times, okay, 9 plus 9 will give us 3, so will give us, uh, square root 9 second square theta times 3 second square theta d theta. Okay, and as you further solve it, you get 3 over 3 tan theta times 3 sec theta, okay, times 3 second square theta d theta. Because you square root, you obviously get the square, right? So here you can notice, if you were to take it out, you'll just simply be resulting to sec theta, right? So you'll just end up having sec theta, okay? And once you have sec theta, all right, and let me just erase this. I'll just erase this first part, by the way, so we'll have a bit of space. So we'll end up having 3 sec theta over 3 tan theta d theta, okay? And one thing about sec theta is just 1 over cosine theta. And tan theta is just sine theta over cosine theta, okay? And I want you guys to remember this, okay? Because we're gonna be using it obviously in simplifying this integral, right? So I'm gonna be raising this part just to clear up space. Okay. So we're left with, and of course, by the way, these trees will cancel out, so it'll just be 1. So it'll quite simply be 1 over cosine theta times cosine theta over sine theta, okay, d theta. So yeah, that's what it is. And of course, you can just cancel out the cosines. So it's left with 1. So you'll be having 1 over sine theta d theta as you integrate. And of course, you can just say this as cosec theta, right? Cosec theta d theta. Now, here's the interesting part. Cosec theta. Do we have an integral for cosec theta? A derivative of it, I would say. Hmm. Let's have a look first because at our table earlier we have an integral of cosec theta. Okay. Oh, okay, we do have an integral, thank God. So if you integrate cosec theta, okay, quite simply, it is just negative ln modulus cosec, okay, cosec theta plus cot theta plus c. But you're not finished yet, okay? Because remember we did substitute theta with x, right? So we need to convert it back. I think the earlier one I forgot to do so because I was quite excited on solving it. So yeah, so it's just simply x over 3, right, equals to tan theta. And don't forget your theta is just simply tan inverse. Okay, tan inverse x over 3. So, to come back to original solution, I'll be erasing all this here real quick. Okay, just so that we have a bit of space, I'd say. Okay, so we're left with what? So your final answer would be something like this. So negative ln modulus cosec. All right, it's going to be quite a messy one. It's going to be cosec tan inverse x over 3. Okay, and of course plus the cotangent. Okay, tan inverse x over 3. Okay, and you have plus c. All right. So one thing about cot, by the way, is that we know that when you say 1 over cot, it's just simply 1 over tan, right? 1 over tan, right? Tan inverse, okay, x over 3, okay? So 1 over tan inverse would just simply mean 1 over x over 3, right? And that would be simply 3 over x, right, in this case. So we can safely actually write more elegant in terms of 3 over x. We can just simply write it like that. So I'm gonna write it like that. So it's gonna be 3 over, oh sorry, uh, using yellow. We're gonna be 3 over x, okay? And for cosec, let's see, cosec is basically 1 over sine, isn't it? It's just simply 1 over sine, you know, tan inverse x over 3, okay? And here's the thing actually, uh, if let's say we're to imagine a triangle, okay, we're imagining a right triangle like this, okay? And we know that basically we have a theta right away, and it's a right angle triangle. So we know that tan is basically TOA, right? So tan is just simply opposite over adjacent. So our opposite is x, our adjacent is 3. Okay, and what is this? This is obviously going to be square root of x squared plus 3 squared. Basically square root of x squared plus 9. Okay, and we know that if we're talking about sine, so sine of that is what? Sine of that is just simply, sine theta is just simply adjacent over hypotenuse, right? It's just simply adjacent over hypotenuse. Yeah, sorry, it's not adjacent, sorry, opposite over hypotenuse, sorry, my apologies. Opposite over hypotenuse, okay. So that will, of course, leave us with x over square root x squared plus 9, okay? So I'm going to erase this, by the way, just to make things a little bit less confusing. Okay, so I'm going to erase this. Right? That's sine theta. Now, what is 1 over that? 1 over that would mean, okay, if we had 1 over sine theta, is just equivalent to saying square root x squared plus 9 over x. So, you can present your result a bit elegantly like this. Like so. So, it would be square root x squared plus 9 over x. And we're going to write it as simply plus the tree of x, okay? And of course, we would end up having the modulus plus c, okay? So erasing all of this just to make it clear. I know the board is a bit messy, but yeah, okay? So this is basically your answer, okay? Of indefinite integral. All right. So yeah. Now let's look at another example. Okay, we're gonna look at another example by the way. And this is going to take from another textbook, because a textbook that I'm using, it doesn't seem to have enough examples, so I'll need to take from a second textbook just to make sure that we're all well practiced. Okay, so let me bring it up. Okay, I already brought it up. Now let's look at the questions. How, where is it? Okay, very good. Okay, that's an interesting question. We're now given a case, okay, it's an indefinite integral still, of sine inverse x cubed over square root 1 minus x squared dx. Okay, so we're supposed to find the answer to it. So using trigonometric substitution, find the indefinite integral to this problem, okay, in terms of x. So I'll let you guys try to pause this video and give it a shot, and later we'll work out together how to solve the problem. Okay, so assuming that you guys have paused the video and tried it out, let's work it out together, this problem, okay? So first things first is to recognize the form. What form is this? So as we can see that our form here, okay, let me just write it in blue color. It's just, I mean, I'm talking about this form here, by the way. Okay, not this one, because this one's a little bit wacky, but we're not going to talk about it right now. Let's talk about the one in blue. Okay, so the one in blue, we can see is just simply a square minus x square. Okay, so when you have a square minus x square, so our x would obviously be a sine theta. Okay, what is our a? So our a obviously is 1. Okay, because we know that a square is 1, so 1 equals to a square. So definitely a is just square root of 1, which is just 1. So hooray. So our x is just simply sine theta. So our dx over d theta is just cosine of theta. Okay. And we know this is 1, by the way, so let me just erase this so that you don't get confused. Okay? Because it's cosine of theta. Okay? And dx is just cosine of theta d theta. Okay. So what's going to happen as we proceed with this integral? Okay. So, of course, as we do the integral, so we have here sine inverse. Okay? X is what? X is just sine theta, right? So we'll have your sine inverse sine theta. Okay? To the power of 3 over square root 1 minus sine square theta. And dx is just cosine of theta d theta. Okay. Oh, one more thing I forgot to mention is that 1 minus sine square theta, by the way. Yeah, we know the identity is just cosine squared theta. Okay. So don't forget the trigonometric identity. So what we have here. Right, so you see that sine inverse sine theta is just equivalent to theta, okay? So there's no need to panic. We end up getting theta cubed. Hooray. And then for here, square root 1 minus sine squared theta is just cosine squared theta times cosine theta d theta, okay? And of course, what does it mean? That would mean that our integral is just theta cubed over cosine theta times cosine theta d theta, and yeah, as you can see, this is obviously you can cancel out, make it a 1, right? So it becomes very straightforward, really child's play. So it's just theta cubed d theta, and of course that's just theta to the power of 4 over 4 plus c. But our job is not done yet. Do not be excited, of course, like what I did earlier and made a mistake. Alright, so of course, remember x is just sine theta, right? But of course, when you want to convert it back to x, let me just erase this real quick. Whoopsie. Okay, I'll make it more clear. Don't be excited. So of course, that would mean what? Our theta would be sine inverse x, right? Sine inverse x. Okay, so our final function. Let me erase this. Do we have space? Can I erase? I'll erase this. Yeah. Our final answer, okay, would be sine inverse x over 4 plus c, and this is to the power of 4. So this is our final answer, okay? So yeah, it may seem intimidating, but once you come with the right trigonometric substitution, as shown here, and you remember the form, at least this form, so if you remember the right substitution that you have to do, then your answer is very straightforward, becomes very magical actually. And that's actually the cool part about integration because there's always a very cool way of solving it. You don't have like a definite way to find the antiderivative and the indefinite integral. Okay, so moving on, we have another question. I'm going to erase this, and this one's obviously about limits. This is involving definite integrals. Right, so let's erase all that. Okay, it's not erased. Okay, cool. So now we have a definite integral, okay? And the limits are between 2 and 0, such nice numbers. And we have your x times, you know, x squared plus 1 dx. Okay. So, of course, by using trigonometric substitution, can we solve this definite integral? I'll give you guys time to pause this video and try to attempt it yourself, actually. Okay, assuming that you guys have paused this video and give it a shot, let's go together. First of all, the first step's always try and recognize the form. So you see our form is basically in this, right? Is just simply x squared plus a squared. Our a in this case is obviously going to be 1, right? So our x would be, let me have a look. Our x would be, x squared plus a squared would be tan theta. Okay, great. So just be tan theta. And our dx over d theta is sec squared theta. Okay, and we know that tan squared theta plus 1 is clearly sec squared theta. Okay, so yeah, with that information we have, we can try to solve the definite integral first, indefinite integral first. So don't worry too much about the limits for now. If you also want to change the limits, we can. So in this case, if we use our calculator to change the limits, because the thing is, uh, theta is obviously tan inverse of x, right? It's a tan inverse of x. So this is the thing you have to keep in mind when you're changing the limits. So in our first case, our tan inverse would be 0, okay? So, oops, sorry, tan inverse 0 is 0, okay? And tan inverse 2 would be, wow, okay. So we're left with 1.1071. Okay. So this is a decimal, but I round off to 4 decimal places. So our x is obviously tan theta, okay, times, of course, tan squared theta plus 1. And our dx is sec squared theta d theta. Okay. So cos 1.1071 0 um tan theta, okay, times of course sec squared theta, and then we have here sec squared theta. d theta. Okay. So square root of sec squared theta would lead us to what? So 1.10710 would have here sec theta times tan theta times sec square theta. Okay, d theta. So now we are given in this form. Okay, our integral is something like this. Okay, and here's the thing actually. Uh, we're also going to do integration by parts. Okay, which I'm going to of course mention in here. So we're going to do integration by parts, like in our first example that we've attempted, right? Integration by, I don't say parts, sorry, by U substitution, sorry. My apologies. U substitution. Okay. So for U substitution, okay, I'm gonna take my U as sec theta. Okay. And of course my du d theta is just sec theta times tan theta. Okay. And du is just sec theta times tan theta times d theta. Okay. And we clearly have those. We already have d theta, we already have sec theta and tan theta. Okay. And of course, we need to change our theta, our u in terms of theta. So of course, sec theta is what? It is 1 over cosine of theta, right? So therefore, our new limits would be, so 1 over cosine, sorry, 1 over cosine 0 would be 1, okay? And 1 over cosine 1.1071 would be, yeah, would be something like this. So 2.2359. So 2.2359. Okay. So sec squared theta is just gonna be u square. Okay, and sec theta, tan theta, d theta is just du. Okay, straight away. So it's very simple. It becomes a very simple integration. So just u cube over 3. Okay. Our limits are from 2.235 2.2359 and 1. So our final answer should be uh hold up, yeah. 2.2351 cube over 3 minus 1 cube over 3. So our final answer should be 3.3926. Okay? So it's our final answer. Okay? So hopefully you guys were able to follow this. Alright, it was not too bad. Now we're going to one last question of the day. So let me just erase this and go to the last question of the day. Oh, sorry. I erase so quick that sometimes I make the board shake. Yeah. So yeah, something really happens. I apologize for that. And yeah, hopefully, okay, cool. So the last integrals, also different integral as well, really cool stuff. So 1 and 0, we're left with x, okay, square root of x squared plus 1 dx, okay. So I'll give you guys the time to pause this video and try to use trigonometric substitution to solve this problem. Okay, so assuming that you guys have tried to solve this problem, the first things first, always recognize the form. So this is the form right away, square root x squared plus 1, which is basically, you can say just a square plus x squared. And if I'm not mistaken, this is obviously, you can use this trigonometric rule, which is x equals to uh a tan theta. Okay. But here's the thing, what is your a? Your a is clearly 1, right? Because a square is 1 square, so a is 1. So therefore x is just simply the tangent of theta. So your dx d theta is just sec square theta. Okay, so dx is just simply sec square theta d theta. Okay, And remember that 1 plus tan square theta, okay, is equivalent to sec square theta, okay? So what we're going to do here, one more thing, yeah, when you're doing definite integration, don't forget to change our limits. So of course we know that theta is just tangent inverse of x, right? So we're changing our limits, making it to, let me just do it real quick. So our limits would now be, let me see here. Yeah, so tan inverse 0 is just 0. And tan inverse 1 is what? 1 over 4 pi. Okay. So it's pi over 4. Okay, great. X is just simply tangent theta. So it's just tan theta over square root tan square theta plus 1 times dx is sec square theta. Okay. D theta. So of course we'll have pi over 4, 0. So just tangent of theta. Okay. So we're left with sec square theta. Okay. Times sec square theta d theta. And of course, as we simplify this, okay, so we're left with tan theta over sec theta, right? Because you take out the square root times sec square theta d theta. And here's the thing, okay? Because if you were to simplify, you just end up having sec theta, right? And then your expression is just nothing more than pi over 4, 0, sec theta times tan theta d theta. And okay, this is obviously the antiderivative of sec theta, and tan theta is clearly, let me check, yeah, let me see, just to double check and be clear. It's just simply, you know, sec theta, right? I'm just double checking. I already know the answer sec theta, but I'm just double checking. Pi over 4 over 0. Okay, great. So I'm gonna erase this part, by the way, so that we have a bit of space. Okay, and now we work on it. So we know that sec theta is just simply 1 over cosine theta, right? So pi over 4 and 0. And what we have here, let's see. So just 1 over cosine pi over 4. Okay, square root 2 minus 1. So yeah, I'm gonna leave it as square root 2 minus 1. So this is your final answer. If you want a decimal answer, for instance, so it's just gonna be 0.4142 in 4 decimal places. So both answers are pretty much acceptable. Of course, this answer is very elegant. It's very, very nice answer to look at. Just square root 2 minus 1. Okay. So yeah, really, it's really nice to present because these numbers are, I would say, quite held in high regard. Square root 2 is an irrational number, very famous irrational number. Okay, it's an irrational number. Okay. And 1 is basically one of the most important numbers, right? Very, I would say in many cases, like for example, in binary, in many applications, okay? So that's why a lot of people, right, math-oriented people, they prefer square root 2 minus 1 as the final answer rather than decimals with 0.4142, which doesn't seem very elegant. But personally for me, both of the answers are completely okay. There's no problem. All right? As long as you show how to get the answer, that's the most important thing. The methodology is more important. Okay? So for the next video, all right, hoping to cover more on partial fractions. Okay? This is the last standard technique for, I would say, integration. Okay, so partial fractions. All right? So we're gonna cover on those in the next video. And yeah, I can't wait. Thanks for watching. Right, and see you guys soon.